So we're back now, and we're going to be titrating a weak acid again with a strong base. You may think to yourself, wait a second, if you watched the first video, didn't we just titrate a weak acid with a strong base? And we even used the same acid, propionic acid. But here's what happened here. In this first scenario, we had a container, and we had the H prop, that's our short way of saying it, in here, and we added OH minus into it. But we added so much OH minus that at the end, all we had left was the OH minus. We didn't have any of the acid left. So when we did the calculations at the end, all we had to worry about was just figuring out what the pH was of the remaining OH. This case, and I don't want to spoil it for us, but we're going to do the same thing. We're going to have our H prop, propionic acid, is going to be sitting in here, and we're going to add OH minus into it, but the OH minus is going to get used up, and we're going to be left over with some H prop, and that's going to leave us with an equilibrium problem. And if you remember, the order always is this. Whenever you're doing an acid or a titration, the first step is you do the stoichiometry. Do the stoich, we often say. And the second step is we do an equilibrium problem. Now, the previous problem, we didn't really do an equilibrium problem because all we had was OH minus left over. But in this case, we're going to end up with some conjugate, and we're going to walk away through it. So let's just actually tackle this problem, and let's remind ourselves that, again, we're dealing with propionic acid, which I never want to write out. So let's just write out the equation so we have it as our go-to for the remainder of this problem. And I'm going to write it as this, H prop. That's in lieu of writing this whole thing out, which is totally fine to do. We're going to throw that into water. And by that, I mean not throw that into water, because for a second, my training kicked in. We're actually going to throw KOH into it. Now, what's kind of important about KOH is that it's really K plus and OH minus, and the K plus is a spectator ion. So really what we're doing here is we're adding OH minus to our H prop. And this is going to be a one-way street, because whenever you have a strong acid or a strong base, in this case we have a strong acid, whenever we have one of those, they're going to completely either use up all of this or they're going to die trying. So we'll end up using up all the OH minus and end up with a little bit of this left over, or the OH minus will completely use up this and we'll end up with extra OH. So it's a one-way street. And what that means is that on the other side, we're going to end up with prop minus plus H2O. Now, this first step, doing the stoichiometry, we have to do it in terms of moles. So I'm going to do initial change and end point here. And the way we deal with moles, whenever we have molarity, molarity is equal to moles divided by volume. But if we rearrange that equation, we have molarity times volume equals moles. Well, that did not work out so well. Now, if we take a look at the actual problem, they give us the volume and they give us the molarity. So that looks like we have both the molarity and the volume. Couldn't we figure out the moles? Now, the other thing I want to point out here is they give us milliliters. And one of the things that we're capable of doing here, and we love doing, is when they give us milliliters and molarity, when we multiply them out, we end up with the fun thing called millimoles. Now, what are millimoles? Well, there are essentially moles divided by 1,000. But at the end, if we have only milliliters, it's going to pop back out to a molarity problem. So if you don't know what I'm saying, let me show you what we're going to do right now. We want to convert this right here to millimoles and put it right here. And then we want to take the OH minus milliliters and the amount, the 66.42, and we want to figure out the millimoles here. So let's start off with our millimoles of our propionic acid. And the way we're going to do that is, since we know that molarity times volume equals moles, we know that 115.5 milliliters, I did this a little bit backwards, should have put the molarity first, times 0.8000 molar. We multiply that out, we end up with 89.2000 millimoles. So that is what our starting amount is here of our H prop, 89.2000. Let's do the same thing now for our OH minus. This is for our H prop. And now we're going to do it for our OH minus. Now, what do we have for OH minus? We have 0.87000 molar, and we have 66.42 milliliters. So when we plug those in, again, our molarity times volume equals our moles. And I'm going to do it the correct way right now. We're going to go 0.8700 molar times 66.42 milliliters. And when we multiply that out, we're going to end up with 57.7854 millimoles, which is what we're going to put back in our overall equation, 57.7854. Now, you may be thinking, I don't want to write all those numbers out, and you could get away with not doing it. The general form is whenever you have significant figures, you carry as many as you can until they finally ask you to answer a question. So if you wanted to go 89.2 here and 57.8, that's totally legitimate. That totally would work. You're going to get only a very slight different answer. So since we have these two things originally, we're going to have 0 of this, and for a liquid, we don't care at all. And I get kind of lazy with writing aqueous in here, but I want you to get in the habit of always writing aqueous in here. So what we know is that we have a strong base. So this is going to react and react and react until either A, it uses up all of this, or B, you have none of this remaining. And because this is a smaller number than this is, we know we're going to end up with H prop remaining, and we're going to end up with nothing of our OH minus. So let's just do the math on this. We're going to subtract the 57.7854 from both of these. And the reason we're going to do that is because the OH is going to 100% subtract out. And when we do that, we're going to end up with extra 31.4146 millimoles of this. We're going to end up with 0 of this. And here's what's really interesting. Over here, we were losing the 57.7 and the 57.7, but over here, we're gaining the 57.7854 millimoles because this is on the product side. So when we do that, at the end, we're going to end up with 57.7854 millimoles of not only our acid, but now we have the same thing of our conjugate base. Now, this is a different beast altogether because we have millimoles over here and we have millimoles over here. The other thing to remember is that we have we've added in both our OH minus to our H prop. So here's our H prop to begin with. And to that, we've added in our OH minus. So we have to calculate the new volume, which is the milliliters of OH minus and the milliliters of H prop added in. And you can do it in one of two places. I like to do it right here because we want to get back to, we've taken care of the stoichiometry, but now we want to take care of the equilibrium problem. So if we take a look at our volumes here, we have 111.5 milliliters of one, and we have 66.42 milliliters of the other. And because we have millimoles here and milliliters here, the millis cancel out, and we end up with a volume of, or a molarity of 0.176566. Again, we're carrying all these numbers out, although you don't really need to. And if we do the same thing over here, and we divide by the same exact number, the 115.5 or 111.5 milliliters and the 66.42, when we divide it out, we end up with 0.324783 molar. Now, what we have right now is we have both an acid and its conjugate base. And so what we can do is we can now do an ice problem by throwing either the acid into water or the base into water. One of the two is going to work. But there's a better way to do this. And the better way to do this is by using the Henderson-Hasselbalch equation. And that only works when you have both an acid and its conjugate base. So I'm going to go ahead and do that right now because I preferably would not want to do this. And by the way, if you have an urge to do the old way of doing it and throwing it into water, you could take your H prop, remember that's your propionic acid, add that to water. And when you do our equilibrium, you're going to end up with prop minus and H3O plus, right? And you could plug these variables in right here, these numbers in here as our initial values here and here. but that is a headache. So what we're going to do is we're going to make it a lot simpler on ourselves, and we're going to use Henderson-Hasselbalch's equation, which is pH is equal to pKa plus the log of AHA, I like to call it, which is the base over the acid concentration. Now, when we do that, we're going to end up with plugging the pKa, and weren't they delightful in this problem? They gave us the pKa in the problem itself. So right here, they gave us the pKa of 4.89. So we can come down here and put the pKa of 4.89 in here. We're going to then take the log of our base, our prop minus, which is 0.324783, all of that on top, divided by 0.176566. Now, I'm going to do this calculation simultaneously right now, and when I do that, I'm going to get 1.839. So when I do the log of 1.839, I end up with 0.2645817, so many numbers after that. And I'm adding that to what my pKa was, 4.89. And when I do that, I end up with my pH equal to 5.154581. Now, this is the correct answer, but when we take a look back up here, they want us to do it to two significant figures. So we're going to round it to two significant figures. But if we were doing this for the AP board, there's four significant figures here, four significant figures here. Here, we have only two significant figures. Remember, this is the pKa. So in reality, ALEKS, they've got it right, even though they normally wouldn't in this case. We need to have only two significant figures, and that means that my final answer here needs to be 5.15. Hopefully this has been helpful.